There are an estimated 300 billion stars in the Milky Way alone. For most of human history, we did not know whether even one of them had a planet. Today, we know of thousands. Among them is a world just 12.5 light years from Earth that has quietly become one of the most compelling places in the search for life beyond our solar system. Its name is Teegarden b. Scientists use something called the Earth Similarity Index to compare distant worlds with our own. The scale runs from 0 to 1, where Earth itself scores 1, Mars scores 0.64, Venus scores 0.44, Teegarden b scores 0.95. No confirmed exoplanet has ever scored higher. It orbits inside the narrow region around its star where liquid water could exist. Its gravity is expected to feel remarkably close to Earth's. A full year there lasts less than 5 days, yet climate models suggest parts of the planet could experience temperatures that overlap with those where life thrives here. Even stranger, the tiny red star it orbits is so faint that astronomers did not even recognize it as one of our closest stellar neighbors until 2003. It had been hiding in plain sight for decades. The system itself may be between 8 and 10 billion years old, giving life there, if it ever began, billions of extra years to evolve beyond anything Earth has produced. And yet, one missing piece of information changes everything. No telescope ever built can tell us whether Teegarden b has an atmosphere. Without one, the planet could be lifeless. With one, it could become one of the strongest candidates for alien life ever discovered. If space content like this is your thing, we've got plenty more. Subscribe, and you'll have a new documentary waiting for you next time you need one. It starts with a star that spent almost all of human history hiding in plain sight, long before anyone searched this region of space for another Earth. A faint point of light had already been crossing the sky above us. You would never have noticed it without careful instruments. Even experienced astronomers overlooked it for decades. That makes its story feel almost improbable, because one of our nearest stellar neighbors spent much of modern astronomy hidden inside plain archival records. In 2003, National Aeronautics and Space Administration astrophysicist Bernard Teegarden was examining older sky survey photographs while searching for near Earth asteroids, objects whose paths might someday cross our own planet. His attention was fixed on moving targets. During that work, one tiny source shifted position between photographic plates. That gradual motion is called proper motion, the slow change in a star's apparent position against far more distant background stars. Nearby stars reveal themselves this way because their closeness makes their movement across the sky measurable over time. The remarkable part came next. That same star had already appeared in astronomical surveys for many years. It had been photographed thousands of times, yet it remained uncatalogued as a nearby star, blending into enormous collections of faint objects that attracted little attention. Its appearance offered almost no hint of its true importance. The explanation rests in the nature of the star itself. Teegarden's star belongs to the family known as red dwarfs, the smallest and faintest true stars capable of sustaining hydrogen fusion within their cores. Fusion is the process where hydrogen atoms combine into helium, releasing the energy that allows stars to shine for immense spans of time. This particular star emits only about 0.073% of the light produced by our sun. To human eyes, it remains completely invisible, but its faintness does not make it unusual. Quite the opposite. Around 70% of all stars in the Milky Way belong to this same red dwarf family. Most of our galaxy is built from stars much like this one, modest in brightness, yet astonishing in number. We often picture brilliant stars dominating the heavens, though the galaxy itself is largely carried by these dimmer companions. Teegarden's star lies only 12.5 light years from Earth, placing it among roughly the 25 closest known stellar systems. If we compressed the entire Milky Way until it stretched across a continent, our Sun and this star would occupy the same room. Cosmic distance still separates them, yet they remain immediate neighbors on the galactic map. Astronomers confirmed the discovery, recorded its properties, and moved on. No planets were known, no remarkable signals appeared. The star settled into scientific catalogs with little expectation of future attention. But one detail already carried extraordinary significance. Teegarden's star is estimated to be between 8 and 10 billion years old. It had already spent billions of years shining before Earth itself was born, preserving an uninterrupted history far older than anything our own world has ever experienced. You never see the planet itself. Every conclusion begins with light arriving from its star, carrying tiny changes that seem almost impossible to notice. We are asked to trust motion far too small for any eye, even one attached to the finest telescope ever built. Yet this is exactly where modern planet hunting becomes extraordinary. The technique is called radial velocity. The name sounds technical, though the idea is surprisingly simple. A planet does not travel around a perfectly fixed star. Instead, both bodies circle a shared center of mass, the balance point created by their combined gravity. The planet follows the larger path. The star traces a much smaller one. Even so, the star never remains perfectly still, but that movement cannot be watched directly across the sky. It is far too slight. Astronomers measure it through the star's light instead. As the star drifts toward Earth, its light becomes compressed, shifting slightly toward the blue end of the visible spectrum. As it drifts away, the light stretches toward the red end. This behavior is called the Doppler effect, the same physical principle that changes the sound of an ambulance siren as it passes you on a nearby road. For Teegarden B, the effect is astonishingly small. The planet causes its star to move at less than 3 meters each second, slower than the pace of an easy jog. Detecting such a minute change across 12.5 light years required remarkable engineering because every measurement had to distinguish a genuine planetary signal from countless competing sources of noise. That achievement belonged to an instrument called the Calar Alto High Resolution Search for M dwarfs, with exo-Earths with near-infrared and optical Echelle spectrographs. It operates at the Calar Alto Observatory in the mountains of Andalusia, Spain. The spectrograph was designed specifically to search for Earth-mass planets orbiting nearby red dwarf stars, where these tiny gravitational motions offer the best chance of discovery. Patience mattered just as much as precision. Researchers gathered 200 separate observations over 3 years. Each observation contributed only one small piece of evidence. Standing alone, a single measurement revealed almost nothing. Together, they gradually uncovered a repeating orbital pattern hidden beneath natural stellar variation and instrumental uncertainty. In June 2019, astronomer Matthias Zechmeister and his colleagues presented the results. They confirmed two planets circling Teegarden's star. The inner world carried an estimated mass of about 1.05 times that of Earth and completed one orbit in only 4.91 days. Those values alone attracted considerable interest, but another figure lingered in the published analysis. The Earth Similarity Index, a comparative scale that measures how closely a planet resembles Earth's physical characteristics, reached an extraordinary value of 0.95. Scientific papers rarely celebrate their own discoveries. This one remained measured and careful. Even so, that single number immediately placed Teegarden B among the most compelling worlds ever identified beyond our own solar system. Distance can be a deceptive guide in the universe. A world that circles extremely close to one star may enjoy conditions remarkably similar to another that travels much farther away. As we continue this journey, you begin to see that location only gains meaning when it is measured against the nature of the star providing the light. Astronomers describe this region as the habitable zone, often called the Goldilocks zone. It is the range of orbital distances where temperatures could allow liquid water to remain stable on a planet's surface, provided other important conditions cooperate. Around our own Sun, this zone extends from roughly 0.95 to 1.37 astronomical units. An astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers, which is about 93 million miles. Earth travels near the inner portion of that favorable region, but Teegarden B follows a completely different arrangement. It circles its star at only 0.0252 astronomical units, roughly 1/40th of Earth's orbital distance. That equals about 3,780,000 kilometers, which is about 2,350,000 miles. At first glance, such an orbit seems certain to produce unbearable heat. The star changes everything. Teegarden's star releases only a tiny fraction of the energy produced by our Sunday. Because its light is so much weaker, the habitable zone contracts dramatically toward the star itself. A planet can travel astonishingly close while still receiving an overall amount of stellar energy, similar to what reaches Earth's surface. The geometry feels unfamiliar, yet the underlying physics remains beautifully consistent across the galaxy. One consequence follows immediately. Teegarden B completes an entire year in only 4.91 Earth days. Before many calendars would even mark the end of a work week, another orbit has already finished. Yet climate calculations suggest the planet may receive an energy balance comparable to our own world, despite that astonishing pace. Another companion circles farther out. Teegarden C completes one orbit in about 11.4 Earth days. Its Earth Similarity Index is estimated near 0.68, placing it noticeably below its inner neighbor. Current models place this planet near the cooler outer edge of the habitable zone, where liquid water on the surface would probably require a dense atmosphere rich enough to trap additional warmth. These orbital positions are among the strongest measurements astronomers possess for the system. They are determined directly from observation rather than speculative climate modeling. We therefore know where Teegarden B travels relative to its star with impressive confidence, but being inside the habitable zone settles only one part of the story. It tells us that the planet receives an encouraging amount of energy. It says nothing about whether that energy can be transformed into an environment where oceans, weather, and perhaps even living systems could endure across billions of years. Imagine standing on a landscape where the position of the star never changes. You could return after a lifetime and find that glowing red sun suspended in exactly the same place above the horizon. Time would pass, seasons might change, yet the sky itself would seem almost frozen into a permanent arrangement. This unusual state is called tidal locking. It develops when gravity gradually synchronizes a planet's rotation with its orbit until both take exactly the same amount of time. Instead of spinning freely like Earth, the planet always presents the same hemisphere toward its star. Teegarden B almost certainly reached this condition because it circles only about 3,780,000 kilometers from its star, which is about 2,350,000 miles. At such a close distance, gravity has immense influence over the planet's rotation across billions of years. We already know an example much closer to home. Earth's moon is tidally locked to our planet. Whenever you look upward, you always see the same lunar face because the moon rotates once during every orbit around Earth. The hidden hemisphere remains permanently turned away from us. On Teegarden B, the same process unfolds, except the star replaces Earth. At first, the consequences appear severe. One hemisphere receives continuous starlight without interruption. The opposite side never experiences direct illumination at all. There are no familiar mornings, no evenings, no daily cycle carrying warmth across the landscape. Such a world seems destined to divide into relentless heat on one side and intense cold on the other. But planetary climates depend on more than sunlight alone. If Teegarden B possesses a substantial atmosphere, moving air could transport enormous amounts of heat across the globe. Winds driven by pressure differences would carry warmth away from the illuminated hemisphere while returning cooler air in an ongoing planetary circulation. Instead of allowing temperatures to separate completely, the atmosphere could soften both extremes into something much more stable. That possibility gives special importance to the region called the terminator. This is the broad boundary where permanent daylight meets permanent darkness. Here, the red star would remain fixed near the horizon, never rising and never setting. Temperatures could become moderate enough for liquid water if atmospheric circulation proved efficient enough to balance the competing influences of light and darkness. The terminator would not be a narrow dividing line. Across a world similar in size to Earth, this transitional region would stretch for thousands of kilometers, which is about thousands of miles, wrapping around the entire planet like an endless belt of twilight. It could become the most favorable environment anywhere on the surface. But this geometry asks us to rethink an assumption carried from our own world. Habitability does not always resemble familiar skies, familiar days, or familiar rhythms. Sometimes an entirely different arrangement of light and motion can still provide conditions where a living world remains physically possible. Even the most promising world can remain at the mercy of the star above it. As we move beyond orbital distance and planetary motion, another influence begins to dominate the story. You cannot see it directly, yet it shapes whether an atmosphere survives long enough for life to gain a lasting foothold. Red dwarf stars possess powerful magnetic fields, especially during their younger years. Those tangled magnetic lines occasionally snap and reconnect, releasing enormous bursts of energy known as stellar flares. A stellar flare is a sudden eruption that can increase a star's emission of high-energy radiation, including X-rays and ultraviolet light, by 100 to 1,000 times within only a few minutes. Events of this kind unfold with astonishing speed. For a planet circling very close to its star, the consequences can become severe. Every major flare sends intense radiation racing across space toward the planetary surface. Earth also experiences space weather from our Sun, yet our much greater orbital distance softens its impact. A similar eruption from a typical red dwarf can expose a nearby planet to radiation levels far beyond those measured during even the strongest solar storms recorded around Earth. But the greatest danger reaches beyond the surface. High-energy radiation breaks apart atmospheric molecules into smaller fragments. Charged particles, carried outward by stellar activity, can then sweep away ionized gases from the upper atmosphere. Ionized gas is ordinary gas whose atoms have gained or lost electrical charges, making them easier for stellar winds to carry into space. Repeated over millions of years, this process can gradually remove an atmosphere almost completely. We have already seen a nearby example that illustrates this concern. Proxima b orbits the closest known star to Earth at roughly 4.2 light years away. Although its size and location attracted tremendous excitement, Proxima Centauri is among the most magnetically active red dwarf stars yet studied. Several independent climate models suggest that repeated flaring may have stripped away much of the planet's atmosphere, assuming one formed in the first place. Teegarden's star appears noticeably different. Observations gathered by the Calar Alto High Resolution Search for M dwarfs with exoearths with near-infrared and optical Echelle spectrographs found far fewer energetic flares than astronomers typically expect from comparable red dwarfs. The star has earned a reputation for unusually gentle magnetic behavior, especially considering its age. That encouraging pattern carries important weight, but it cannot guarantee safety. Stars change over time, and even an infrequent, powerful flare can influence a nearby planet. The radiation threat remains real. One additional shield may exist. If Teegarden B possesses a magnetic field generated by a rotating liquid iron core, that invisible barrier could divert many charged particles before they reach the atmosphere, much as Earth's magnetic field protects our own world every day. Whether such a shield surrounds Teegarden B remains completely unknown, leaving one of the most important pieces of the puzzle still beyond our reach. Every measurement we have followed until now leads toward a single unknown. You can compare gravity, calculate orbital distance, estimate stellar energy, and model planetary winds with remarkable confidence. Yet one missing ingredient still decides whether those encouraging numbers describe a living world or nothing more than bare stone beneath a distant red sky. Does Teegarden B possess an atmosphere? Everything changes with that answer. Without an atmosphere, the planet's estimated surface temperature would remain near negative 47 degrees Celsius or negative 53 degrees Fahrenheit, controlled almost entirely by the energy arriving from its star. With an atmosphere similar in strength to Earth's, climate models suggest average surface temperatures could instead range from about 0 degrees Celsius or 32 degrees Fahrenheit to roughly 28 degrees Celsius or 82 degrees Fahrenheit. Those differences determine whether liquid water can remain stable, whether heat spreads around the globe, and whether complex chemistry has enough time to continue for billions of years. Astronomers usually search for atmospheres through a technique called transmission spectroscopy. The method depends on a fortunate alignment. When a planet passes directly across the face of its star from Earth's viewpoint, an event called a transit, a tiny fraction of starlight travels through the thin outer layers of the atmosphere before reaching our telescopes. Different gases absorb different wavelengths of light, creating recognizable chemical fingerprints. By examining those patterns, researchers can infer which molecules surround a distant world. But Teegarden B never crosses its star from our perspective. Its orbital geometry simply does not line up with Earth. Since no transit occurs, that entire observational method becomes unavailable. One of the most productive techniques in modern planetary science cannot be used for this remarkable world. Even the James Webb Space Telescope faces this limitation. Since its launch in December of 2021, it has transformed the study of distant planetary atmospheres through unprecedented sensitivity. Yet its greatest strength depends on transiting planets. Teegarden B offers no such opportunity, leaving one of astronomy's most capable observatories unable to answer the question we care about most. Several possibilities remain physically realistic. The planet may possess little more than a thin trace of gas, leaving the surface exposed to radiation and severe temperature contrasts. It could instead hold a dense atmosphere rich in carbon dioxide, trapping heat so efficiently that conditions become hostile despite its favorable orbit. Or it may carry an atmosphere dominated by nitrogen and oxygen, allowing liquid water and long term climate stability similar to Earth's. Venus reminds us why this distinction matters. Although it occupies the Sun's habitable region, its massive carbon dioxide atmosphere drives surface temperatures to about 465 degrees Celsius or 869 degrees Fahrenheit. The orbit alone never tells the whole story. The atmosphere decides how a planet truly lives beneath its star. Across one of the driest landscapes on Earth, workers are assembling a machine whose purpose reaches far beyond our own world. High in Chile's Atacama Desert, each polished segment placed into position brings us closer to reading the chemistry of a planet we cannot yet fully understand. Progress arrives piece by piece. This observatory is called the Extremely Large Telescope. Its primary mirror will measure 39 meters across, which is about 128 feet, making it the largest optical telescope ever constructed. First light is presently expected around the year 2028. Every increase in mirror size allows astronomers to collect more light, and more light reveals details that once disappeared into darkness. Among the observatory's planned instruments is the Armazones High Dispersion Echelle Spectrograph, previously known as the High Resolution Spectrograph. A spectrograph separates incoming light into its individual wavelengths, much like a prism spreading sunlight into a rainbow. Within those separated colors, molecules leave distinctive absorption patterns that reveal their presence from extraordinary distances. But this instrument approaches the problem differently. Instead of waiting for a planet to pass across its star, it searches for light reflected directly from the planet itself. That reflected glow carries information about both the surface and the atmosphere. If successful, astronomers could search for water vapor, oxygen, carbon dioxide, methane, or discover that none of those gases are present at all. Teegarden B is especially well suited for this method because its orbital geometry prevents the traditional transit technique from working. The scale of the telescope makes this possible. Its mirror will provide approximately 978 square meters of light collecting area, which is about 10,527 square feet. That enormous surface can gather more light from a distant target in a single hour than previous generations of ground-based telescopes could often accumulate during an entire night of observation. Another observatory is also taking shape, although its launch remains farther away. The National Aeronautics and Space Administration is developing the Habitable Worlds Observatory, a future space telescope designed specifically to detect rocky planets around nearby stars and study their atmospheres directly. Current planning places its launch no earlier than the later years of the 2030s. Teegarden B already appears among the worlds considered especially valuable for that future mission. It is close enough, physically suitable enough, and scientifically compelling enough to deserve careful attention once these instruments become available. For you, this timeline carries an unusually personal scale. Someone watching tonight, in their 20s or 30s, may still witness the first atmospheric measurements arriving from this distant world. The answer already exists within the light, leaving Teegarden B. We simply stand at the point in history where our instruments are finally approaching the sensitivity needed to read what has been traveling toward us all along. Numbers can feel reassuring. They compress enormous amounts of information into a single value that seems easy to understand. But every scientific number carries boundaries. and you only appreciate its meaning after understanding what was intentionally left outside the calculation. The Earth Similarity Index was created as a comparison tool rather than a declaration that a planet can support life. It helps astronomers rank newly discovered worlds according to how closely their measurable physical characteristics resemble Earth's. That ranking allows researchers to decide which planets deserve deeper investigation as better instruments become available. The calculation combines four different properties into one overall score using a mathematical method called a geometric mean. A geometric mean blends several measurements while preventing any single value from dominating the final result. The first property is planetary radius, compared with Earth's radius of about 6,371 kilometers, which is about 3,959 miles. The second is bulk density, a measure of how much material is packed into a given volume. The third is escape velocity, meaning the speed required for an object to overcome the planet's gravity completely. The fourth is the estimated surface temperature under assumed conditions. Across those four categories, Teegarden B performs remarkably well. Its estimated radius is about 1.02 times that of Earth. Its inferred density suggests a rocky composition similar to our own world. Its escape velocity appears almost identical. Climate models using an Earth-like atmosphere also place its estimated equilibrium temperature within a familiar range. Together, those similarities produce the remarkable Earth Similarity Index value of 0.95. But the calculation deliberately ignores several of the questions we care about most. It does not measure atmospheric thickness or chemical composition. It says nothing about whether oceans actually exist. It cannot determine whether the planet possesses a magnetic field protecting its surface from charged particles. Geological activity also remains outside the calculation, even though volcanism and plate tectonics help regulate Earth's climate over immense stretches of time. The surrounding radiation environment receives no direct weight either, nor does the planet's rotational state, including tidal locking. Those omissions matter enormously. The Earth Similarity Index describes the framework of a potentially habitable world, yet many of the conditions that determine whether life can emerge or endure remain completely separate from the score itself. Mars provides an excellent reminder. It achieves an Earth Similarity Index of about 0.64, encouraging enough that scientists have devoted generations of exploration to searching for signs of ancient or present life. Even so, Mars remains cold, possesses only a thin atmosphere, and receives intense radiation at its surface. The value of 0.95, therefore, should never be mistaken for evidence that Teegarden B is inhabited. It simply tells us that, among all confirmed planets discovered beyond our solar system, none has passed this initial physical comparison more convincingly. The score opens the correct door. We still have to discover what lies beyond it. Some planetary properties influence every moment of existence without ever being seen. Gravity belongs to that hidden group. You cannot hold it, yet every movement, every growing branch, every flowing river, and every beating heart responds to its constant pull from the instant life begins. Current measurements suggest that Teegarden B possesses about 1.05 times Earth's mass. That value lies so close to our own planet that the remaining difference falls within the uncertainty of present observations. From this estimate comes another remarkable result. The surface gravity is expected to be approximately 0.99 times that experienced on Earth. If you could stand there, your body would scarcely notice the change. But gravity shapes much more than the sensation of weight. It provides the structural framework within which biology evolves. Every living organism must solve the same engineering problems imposed by gravity. Trees can grow only until their trunks can no longer support their own mass. Bones must remain thick enough to carry bodies through daily movement. Blood must climb upward from the heart toward the brain against a constant downward pull. Even tiny droplets moving through microscopic tissues behave according to the surrounding gravitational environment. We already know how strongly life responds when gravity changes. Mars possesses only about 0.38 times Earth's surface gravity. Astronauts living for extended periods under such conditions experience measurable losses in bone density and muscle strength, while the cardiovascular system gradually adapts to a weaker gravitational pull. The human body evolved under one particular environment, and it begins adjusting whenever that environment changes. Teegarden B appears strikingly different. A world with gravity, almost identical to Earth's, would place nearly the same mechanical limits on any organisms that emerged there. This does not suggest that alien life would resemble familiar plants or animals. Evolution follows countless, unpredictable paths. Yet the physical constraints governing movement, support, circulation, and growth would be surprisingly similar because the underlying force shaping those systems would differ very little from what you experience every day. Mass also provides clues about the planet's hidden interior. Based on its measured properties, astronomers believe Teegarden B is most likely a rocky world composed largely of silicate minerals surrounding an iron-rich core, much like Earth, Venus, Mars, and Mercury. Such an internal structure increases the possibility of volcanic activity that releases gases into the atmosphere, long-term geological recycling through plate tectonics, and perhaps a molten metallic core capable of generating a protective magnetic field. But each of those possibilities still awaits confirmation. They remain informed scientific expectations rather than direct observations. One pattern nevertheless continues to emerge. Whether astronomers measure mass, gravity, density, or overall physical structure, Teegarden B repeatedly returns values that cluster remarkably close to Earth's. Discoveries rarely align so consistently across independent measurements, which explains why this distant world continues attracting such extraordinary scientific attention. Before we imagine forests, coastlines, or unfamiliar living creatures, another question waits beneath them all. Does Teegarden B possess water? Every possibility explored so far eventually returns to that single requirement, because life, as far as we know, depends upon a liquid capable of carrying chemistry from one reaction to the next. Water fills that role with remarkable efficiency. It dissolves an extraordinary variety of substances, allowing molecules to meet, combine, and separate with ease. It remains liquid across a broad range of temperatures. Even its behavior when frozen proves unusually helpful. Ice expands instead of contracting, allowing it to float above liquid water rather than sink, preventing entire lakes or oceans from freezing solid from the bottom upward. Countless biological reactions also depend directly upon water itself, making it an active participant rather than a passive setting. But whether Teegarden B possesses water depends upon events that unfolded billions of years before any potential ocean could have formed. Planetary history begins with dust, gas, collisions, and time. Where a planet grows inside its young planetary system determines the materials available during its earliest construction. Teegarden B almost certainly formed well inside what astronomers call the frost line, the distance from a young star beyond which temperatures become low enough for water ice to condense onto solid material. Inside that boundary, conditions remain too warm for ice to accumulate efficiently. A rocky planet forming there does not automatically begin its existence with abundant water locked inside its building blocks. Our own planet likely faced the same challenge. Earth also formed inside the frost line surrounding the Sunday. The leading explanation proposes that much of Earth's water arrived later through countless impacts from water-rich asteroids and perhaps comets that originated farther from the young Sunday. The immense gravitational influence of the giant outer planets gradually disturbed those smaller bodies, sending many inward over hundreds of millions of years until the growing terrestrial planets accumulated vast reservoirs of water. Could the same process have unfolded around Teegarden's star? It remains entirely possible. If distant icy bodies formed within that planetary system and later migrated inward through gravitational interactions, they may have delivered water to Teegarden B in a similar fashion. But the complete architecture of that distant system has not yet been mapped well enough to answer this with confidence. Surface oceans are only one possibility. Geological heat trapped inside a rocky planet can preserve liquid water beneath an icy crust for immense spans of time. We believe this occurs beneath the frozen shells surrounding Jupiter's moon Europa and Saturn's moon Enceladus, despite both worlds lacking substantial atmospheres. Their hidden oceans continue to rank among the most compelling environments for possible microbial life within our own planetary neighborhood. For Teegarden B, the final answer still waits inside its unseen atmosphere. Detecting water vapor through atmospheric spectroscopy would provide the strongest evidence yet, but no existing instrument can perform that measurement for this particular world. Until that day arrives, every ocean on Teegarden B remains a scientifically plausible possibility rather than an observed reality. Life does not adapt to our expectations, it adapts to physics. If living organisms ever emerged on Teegarden B, every feature they possessed would reflect the conditions surrounding them rather than familiar patterns carried over from Earth. We can follow those constraints carefully, allowing chemistry and biology to guide the possibilities without stepping beyond established science. The star illuminating Teegarden B shines very differently from our Sunday. With a surface temperature of roughly 2,900 Kelvin, it releases most of its energy as near-infrared light, consisting of wavelengths longer than those visible to human eyes. Visible light still exists, but it contributes far less energy than the infrared glow that dominates the planet's surface. Any organism gathering energy from starlight would evolve under this different balance. On Earth, plants rely on chlorophyll, a pigment that absorbs mainly red and blue light while reflecting green, giving forests and grasslands their familiar color. But chlorophyll evolved beneath the spectrum produced by our own Sunday. Around a cool red dwarf star, different pigments would likely prove more efficient because they could harvest the abundant infrared radiation instead of leaving much of it unused. Research published in the journal Astrobiology has explored this possibility through detailed biological modeling. The results suggest that photosynthetic organisms surrounding red dwarf stars might absorb almost every available wavelength reaching their surfaces. To human eyes, such organisms could appear black or perhaps an extremely deep shade of red, their surfaces capturing nearly every photon instead of reflecting bright colors back into the landscape. But infrared light introduces another challenge. Each infrared photon carries less energy than a photon of visible blue light. Every individual photosynthetic reaction, therefore, begins with a smaller energy budget. Organisms might compensate by developing remarkably efficient molecular systems, performing larger numbers of reactions, or simply operating through slower metabolic rhythms that demand less energy over time. The absence of an ordinary day and night cycle would shape biology just as profoundly. Along the broad terminator region, the star would remain fixed near the horizon forever. There would be no sunrise announcing morning, and no sunset signaling evening. Without changing daylight, biological clocks would likely respond instead to subtle variations in temperature, atmospheric circulation, humidity, or seasonal changes produced by the planet's orbit rather than by its rotation. The foundation of such an ecosystem could resemble an immense dark living carpet stretching across the twilight zone. Instead of trees reaching upward beneath an overhead sun, broad absorbing surfaces might remain permanently oriented toward the distant crimson glow, resting along the horizon. Every generation would inherit that same direction, unchanged across countless lifetimes. Should complex multicellular organisms eventually evolve, they would encounter surface gravity remarkably similar to Earth's. Their bodies would not require dramatically different structural support simply to stand or move, but their senses, behaviors, and internal rhythms would emerge beneath a fixed sky, shaped by an environment where light never travels across the heavens, yet life could still find enduring ways to flourish. Some planetary characteristics reveal themselves immediately through mass, orbit, or distance. Others reveal their importance only when measured against time. The age of Teegarden's star belongs to that second category because it transforms every possibility we have considered into something far more profound. Astronomers estimate that this small red dwarf is between 8 billion and 10 billion years old. The uncertainty exists because low-mass stars change so gradually that determining their ages with precision remains exceptionally difficult. But even the youngest plausible estimate places the system at nearly twice the age of our own Sun, which formed about 4,600,000,000 years ago. If Teegarden B formed alongside its parent star, it has existed through roughly 8 billion years of uninterrupted planetary history. But what can biology accomplish across such an immense span? Earth offers the only timeline we can study directly. Evidence preserved within ancient zircon crystals and carbon signatures discovered in rocks from Greenland suggests that life emerged surprisingly early, perhaps within the planet's first 500 million years, and certainly within its first billion years. Once chemistry crossed the threshold into biology, evolution began its long and patient work. Progress afterward unfolded unevenly. The transition from simple cells into cells containing nuclei, known as eukaryotic cells, required approximately another 2 billion years. That single step consumed more time than almost any other major transformation in Earth's biological history. Multicellular organisms eventually emerged after roughly another 1,500,000,000 years, opening entirely new pathways for increasing complexity. But the familiar story of animals occupies only the smallest fraction of Earth's existence. The remarkable diversification, often called the Cambrian explosion, began about 541 million years ago. Every fish, forest, dinosaur, flowering, plant, mammal, and human belongs within that comparatively recent chapter. All complex animal evolution, together with every extinction and recovery, fills only about the final 12% of Earth's current age. Now consider the same biological timetable unfolding on Teegarden B. If life appeared there on a comparable schedule, and if environmental conditions remained favorable across billions of years, the equivalent of Earth's animal era would have begun roughly 3,500,000,000 years ago. At that distant moment, Earth itself had not yet produced complex cells. Our planet remained inhabited only by simple, microscopic life. But time alone guarantees nothing. Evolution requires opportunity as much as duration. Catastrophic radiation, atmospheric collapse, chemical instability, or countless other barriers could halt biological progress long before complexity appears. We simply do not know whether Teegarden B followed Earth's path, diverged from it, or never entered it at all. Even so, the age of this ancient system changes the scale of our thinking. Every unanswered question now stretches across almost twice the history of our own world. Whatever processes unfolded there, whether geological, atmospheric, or biological, have had billions of additional years to develop. That extraordinary span of time may be the most understated, yet most astonishing fact in the entire story. Long before Teegarden B became a compelling candidate for careful comparison, another planetary system had already transformed the search for life beyond our own world. In February of 2017, the National Aeronautics and Space Administration announced the discovery of 7 confirmed rocky planets orbiting a single red dwarf star known as TRAPPIST-1, located about 39 light-years from Earth. 3 of those planets occupied the system's habitable zone, immediately making the discovery one of the most celebrated moments in modern astronomy. The excitement was understandable. Never before had astronomers identified so many Earth-sized worlds gathered around one small star. Observatories across the world turned toward the system. Years later, after the successful commissioning of the James Webb Space Telescope, several of its earliest exoplanet investigations focused on those same distant planets because they offered an extraordinary opportunity to examine alien atmospheres. But the first detailed results challenged many expectations. Observations published during 2023 examined the innermost planets, TRAPPIST-1b and TRAPPIST-1c. By measuring thermal emission, which is the heat naturally radiated from a planetary surface, astronomers found no evidence for thick atmospheres surrounding either world. Their temperatures matched what would be expected from exposed, rocky surfaces, rather than planets wrapped in dense gases capable of transporting heat across their landscapes. Those findings did not eliminate the remaining 5 planets from consideration. The inner pair had always been regarded as the least promising candidates for long-term habitability because of their intense stellar heating. But the observations carried a broader message. Simply occupying a favorable orbital distance does not guarantee that a planet retains the atmosphere needed to support stable surface conditions. But that lesson becomes especially important when we return to Teegarden B. The central question is no longer whether the planet circles within the habitable zone. Its orbit has already answered that. The greater uncertainty is whether billions of years have allowed it to preserve an atmosphere against the relentless effects of stellar radiation. That outcome depends upon several interconnected factors, including the star's flare history, the strength of any planetary magnetic field, and the amount of atmosphere present from the beginning. Another difference deserves careful attention. TRAPPIST-1 lies roughly 39 light-years away, more than 3 times farther than Teegarden's star. More importantly, observations indicate that TRAPPIST-1 is a substantially more active flare star. Teegarden's star has instead shown comparatively gentle magnetic behavior, producing fewer and weaker flares than many similar red dwarfs. That calmer history may have given any surrounding atmosphere a greater chance to survive across immense spans of time. But comparison does not provide certainty. Different stars evolve differently. Planetary systems assemble through unique sequences of collisions and migration, Atmospheric histories rarely follow identical paths. The story of Trappist 1, therefore, serves neither as a warning that condemns Teegarden B, nor as reassurance that guarantees success. Instead, it sharpens our focus upon the single unanswered question that continues to outweigh every other possibility, whether this nearby world still possesses the atmosphere that could make everything else matter. Imagine that, many years from now, the atmosphere of Teegarden B finally comes into view. The first spectra arrive, carrying faint patterns hidden within reflected starlight. We would not begin by searching for cities, forests, or unmistakable signs of civilization. We would begin with chemistry. Every narrow dip in that spectrum would represent molecules absorbing particular wavelengths, creating a fingerprint that scientists can compare against laboratory measurements made here on Earth. A biosignature is the name given to a chemical compound or measurable physical property that is extremely difficult to explain through geology or chemistry alone. In simple terms, it is an atmospheric clue whose most straightforward explanation involves biology. That does not make it proof. It makes it evidence deserving careful examination. The distinction matters because planets often surprise us, and nature frequently discovers pathways we had not imagined. The best known target is oxygen. On Earth, about 21% of the atmosphere consists of oxygen, and almost all of it exists because photosynthetic organisms continually replenish it. Photosynthesis is the biological process that uses light to convert water and carbon dioxide into chemical energy while releasing oxygen. Without that endless renewal, oxygen gradually reacts with rocks and minerals across the surface over geological timescales lasting only a few million years. Most of it would disappear. But oxygen rarely stands alone. Ozone forms naturally when oxygen molecules interact with energetic radiation in the upper atmosphere. Its chemical fingerprint appears strongly at ultraviolet wavelengths, providing another valuable line of evidence. Detecting ozone would strengthen the case that oxygen is present in significant amounts, even if oxygen itself proved more difficult to measure directly. Another combination attracts even greater attention. Methane and oxygen rapidly react with one another, steadily removing both gases from an atmosphere. Their long-term coexistence, therefore, requires continual replenishment. On Earth, methane is produced largely by microorganisms living without oxygen, while oxygen comes primarily from photosynthetic life. No confirmed geological process has demonstrated the ability to sustain both gases together at comparable levels for immense spans of time. Scientists would also examine rarer compounds. Nitrous oxide is generated on Earth almost entirely by microbial activity within soils and ocean environments, making it an especially intriguing candidate. Phosphine attracted worldwide attention after a disputed claim involving Venus during 2020, yet, on rocky planets, it remains closely associated with biological production in oxygen-poor environments because no confirmed non-biological mechanism has been shown to create abundant concentrations. But every potential discovery would face extraordinary scrutiny. Independent observatories would need to confirm the same signal using different instruments and different analytical methods before any scientific consensus emerged. Extraordinary claims require repeated verification. They always have. Today, no biosignature has been detected from Teegarden B. Even so, the list of molecules worth seeking is already well defined, the observing strategies already exist, and the telescopes now taking shape have been designed with exactly this challenge in mind. The search has moved beyond imagination into engineering, patiently waiting for the first unmistakable light. Sometimes the deepest scientific mystery begins with an ordinary conversation. During the year 1950, while sharing lunch at the Los Alamos National Laboratory, the physicist Enrico Fermi suddenly asked a question that redirected decades of scientific thought. If intelligent life is common throughout the universe, where is everybody? That single sentence became the foundation of what we now call the Fermi paradox, a puzzle that remains unresolved despite generations of astronomical discovery. The arithmetic behind the paradox appears remarkably simple. Our Milky Way galaxy is about 13.6 billion years old, providing immense stretches of time for civilizations to emerge. Even if an advanced society traveled at only a modest fraction of the speed of light, spreading gradually from one neighboring star to another, it could have crossed the galaxy many times within roughly 1 billion years. Compared with the age of the galaxy, that journey represents only a brief chapter. The numbers seem difficult to escape. But the sky offers a different story. We have searched across radio waves, visible light, infrared radiation, ultraviolet light, and many other portions of the electromagnetic spectrum. We have built larger telescopes, more sensitive receivers, and increasingly sophisticated computer systems to recognize artificial patterns. Yet no confirmed evidence of extraterrestrial intelligence has appeared, no unmistakable signal, no engineered structures, no transformed planetary atmospheres whose chemistry clearly reflects technological activity. Teegarden B occupies an unusually personal place within this mystery. At a distance of roughly 12.5 light years, any radio transmissions sent from that system during the early years of our own broadcasting age would already have crossed our solar system. The reverse is equally true. If we transmitted a directed message toward Teegarden's star today, it would arrive after about 12.5 years. Cosmic communication, at least in principle, falls within a human lifetime. But that possibility should not be confused with observation. Search for extraterrestrial intelligence programs have included Teegarden's star within broader sky surveys, yet no prolonged campaign has focused exclusively on listening to that nearby system across extended periods. A brief absence of evidence tells us remarkably little. Detecting an intentional transmission requires looking at the correct frequency during the correct moment while the source is actively transmitting. Two broad explanations continue to dominate scientific discussion. Perhaps intelligent civilizations are extraordinarily rare because one critical evolutionary step almost never occurs. Or perhaps technological societies arise frequently but remain undetected because they communicate differently, choose not to broadcast, disappear before expanding very far, or employ methods beyond our current understanding. Each possibility reshapes humanity's place in the cosmos. But every improvement in our ability to observe nearby worlds gives the paradox another opportunity to answer itself. If Teegarden B continues to reveal nothing after our instruments become capable of truly listening, its enduring stillness will become one more carefully measured piece of evidence, gently adding weight to one of the greatest unanswered questions in all of science. Long before thousands of planets were discovered beyond our own solar system, one scientist tried to organize a question that seemed almost impossible to approach. During the year 1961, astronomer Frank Drake gathered researchers at Green Bank in West Virginia and wrote a simple equation across a whiteboard. It was never intended to produce a final answer. Instead, it divided an overwhelming mystery into smaller scientific questions that could gradually be investigated one by one. The equation begins with the birth of stars. It then considers how many of those stars possess planetary systems, how many planets occupy environments that could permit liquid water, how often life begins, how frequently intelligence emerges, whether intelligent species develop technology capable of communication, and finally, how long such civilizations remain detectable. Multiply those factors together, and the result estimates how many communicating civilizations may exist within the Milky Way at this moment. When Frank Drake first introduced the equation, almost every term rested on educated guesswork. Astronomers had not yet confirmed a single planet orbiting another ordinary star. Entire categories of information simply did not exist. The equation therefore served as a guide for future research rather than a completed calculation. But decades of discovery have steadily transformed its opening terms. The Milky Way now appears to produce roughly between 1 and 3 new stars each year. Observations from modern planet hunting missions have revealed that planets are remarkably common. Current evidence suggests that nearly every star hosts at least one planetary companion. Studies of red dwarf systems further indicate that roughly 40% may possess at least one rocky world orbiting within the habitable zone, where temperatures could allow liquid water under suitable atmospheric conditions. This is where Teegarden B becomes more than an interesting destination. It becomes a measured value inside the equation itself. We are no longer discussing hypothetical worlds. We have identified a confirmed rocky planet orbiting at an appropriate distance around a nearby star. Whatever uncertainty remains about its atmosphere or surface, it satisfies the physical criteria required to count as one of the galaxy's genuine habitable zone candidates. But the later terms remain almost entirely unconstrained. We still cannot answer the simplest sounding question of all. Given a planet with favorable conditions, how often does life actually begin? If biology emerges almost whenever circumstances allow, then worlds like Teegarden B may already host living ecosystems. If the origin of life is an event of extraordinary rarity, then even a planet resembling Earth in many physical respects could remain forever barren. From there, the uncertainties become even greater. Does intelligence commonly evolve, or is it an exceptional accident? Does technology inevitably appear, or do many intelligent species follow different paths? How long do technological civilizations survive before disappearing or changing beyond recognition? Every unanswered step widens the range of possible outcomes. We still possess only one confirmed example of a living world. Earth remains both our entire sample and our greatest limitation. But Teegarden B has transformed one piece of the Drake equation from speculation into observation, bringing us slightly closer to learning which of its remaining unknowns truly shape the universe. An unexpected idea waits near the end of this journey. It does not begin with astronomy alone, but with philosophy reaching toward the stars. Philosopher Nick Bostrom proposed that the most unsettling discovery humanity could make might not be evidence that we are alone. It could be the confirmation that life exists somewhere else. At first, that conclusion feels completely backward, but the reasoning grows more compelling the longer we follow it. The argument begins with the same puzzle we have already encountered. Intelligent civilizations appear absent across a galaxy old enough to have produced many of them. This absence suggests that somewhere between lifeless chemistry and a civilization capable of spreading among the stars lies an obstacle of extraordinary difficulty. Bostrom called this obstacle the Great Filter. In plain language, it is a step that almost no civilization successfully crosses. Everything depends on where that barrier exists. If the great filter lies deep in the past, then perhaps the hardest achievement was the appearance of life itself. It could have been the emergence of the first self replicating molecules, the evolution of complex cells containing a nucleus, or another ancient transition we still do not fully understand. If that is true, then humanity has already passed through the rarest gateway. The future, while uncertain, may remain largely open, but another possibility carries a very different message. Suppose simple life appears readily wherever suitable conditions exist. Suppose intelligence also emerges with reasonable frequency, followed by technology. If civilizations repeatedly vanish before expanding beyond their home systems, then the great filter has not been left behind. It waits ahead. Somewhere beyond our present level of development, nearly every technological society encounters the same fatal barrier. This is where Teegarden B becomes more than another promising planet. Imagine that future observations reveal convincing evidence of even microscopic organisms. Such a discovery would immediately show that life can arise on separate worlds under favorable conditions. The earliest biological step would no longer appear exceptionally rare. The great filter would shift farther along the chain of events toward intelligence, advanced technology, or another stage we have yet to recognize. That possibility carries profound consequences. But consider the opposite outcome. Imagine that Teegarden B possesses an atmosphere, liquid water, stable conditions lasting billions of years, and gravity remarkably similar to our own, yet remains completely sterile. Such a result would point toward the origin of life itself as the rare event. We would have crossed an astonishing threshold that almost no planet ever reaches. The enduring stillness surrounding nearby stars would become less mysterious and far less ominous. Either conclusion reshapes our understanding of existence. One reveals a universe where living worlds may be widespread, while advanced civilizations remain exceptionally fragile. The other suggests that biology itself is the extraordinary achievement, making every forest, every ocean, and every living cell on Earth part of a rarity beyond measure. But whichever answer nature ultimately gives, Teegarden B may become one of the worlds that finally allows us to hear it. Some scientific ideas seem almost too expansive to examine comfortably. Panspermia is one of them. At first hearing, it resembles a story carried by imagination rather than evidence. Yet the hypothesis has earned careful discussion within astrobiology because every major step in its physical mechanism exists somewhere in nature. The uncertainty lies in whether those verified steps can connect into a successful chain across the enormous distances separating the stars. Panspermia proposes that life, or the chemical ingredients that eventually become life, may travel beyond the world where they first appeared. Tiny microorganisms, dormant spores, or complex organic compounds could become trapped inside fragments of rock blasted away during immense asteroid impacts. If those fragments escape a planet's gravity, they may leave their home system entirely and begin an interstellar journey lasting millions of years. The concept sounds extraordinary. The physics does not. We already know that powerful impacts can launch planetary material into space. Rocks originating on Mars have been identified on Earth after surviving ejection, space travel, and atmospheric entry. Similar events almost certainly occurred throughout the violent youth of countless planetary systems. Material escapes, some of it never returns. But once those fragments drift into interstellar space, the challenge becomes survival across distances that stretch almost beyond comprehension. Experiments have shown that some forms of life possess remarkable endurance. Tardigrades, microscopic animals found from Antarctic ice to deep ocean hydrothermal vents and high Himalayan mountains, can survive the vacuum of space, temperatures approaching absolute zero, and radiation levels fatal to nearly every other known animal. Certain bacterial spores have also endured years in orbit while remaining capable of revival after returning to more favorable conditions. These discoveries reveal unexpected resilience. They do not guarantee endless survival. The voyage from Teegarden's star to our own solar system would likely require millions, perhaps tens of millions, of years at the speeds expected for naturally ejected debris. That interval greatly exceeds any survival time demonstrated under experimental conditions. But the earliest history of a planetary system is especially turbulent. Giant collisions occur more frequently. Vast quantities of rock are launched into surrounding space. During those same ancient ages, biology, if it exists at all, may also be taking its first uncertain steps. The timing is remarkably suggestive. This possibility changes how we think about neighboring worlds. If panspermia has ever operated, even rarely, then nearby planets may not represent completely separate experiments. They could share an ancestral chemistry carried across space long before either world resembled its present form. We might eventually discover organisms that appear unfamiliar in every visible way, yet still rely upon molecular foundations inherited from the same ancient cloud of gas and dust that gave birth to both stellar families. But until evidence replaces speculation, panspermia remains an intriguing bridge between established physics and one of the deepest questions we can ask about our own origins. Sometimes, the greatest change in science begins with a shift in attention rather than a new discovery. For generations, astronomers looked toward the brightest stars because those were the easiest to observe with the available instruments. The faint red dwarfs, scattered across the sky, remained in the background, appearing too dim, too small, and too ordinary to occupy the center of humanity's search for living worlds. That preference shaped decades of research. Our own planet circles a yellow star. So many scientists naturally assumed similar stars would offer the most promising places to seek life elsewhere. The reasoning seemed sensible. Earth provided the only confirmed example of biology, and its circumstances became the template. But assumptions built from a sample of one can guide an entire field for years before anyone asks whether another path deserves equal attention. As observational techniques steadily improved, the picture changed. Smaller planets became detectable around smaller stars because their gravitational influence was easier to measure. Each new survey revealed another rocky world orbiting a red dwarf, and the numbers gradually became impossible to ignore. We were no longer studying an unusual class of stars. We were confronting the dominant population of our galaxy. Red dwarf stars account for roughly 70% of all stars in the Milky Way. Astronomers estimate there are between 160 billion and 200 billion of them spread across the galactic disk. If only a modest fraction host rocky planets within regions where temperatures could permit liquid water, the total number of potentially habitable worlds exceeds the number of human beings who have ever lived by an astonishing margin. But statistics alone do not confirm living planets. They reveal opportunity. This realization inspired new instruments with a different purpose. The Calar Alto high-resolution search for M dwarfs with exoearths, with near-infrared and optical Echelle spectrograph survey, commonly known by its established project name, Carmenes, was designed specifically to search for planets around nearby red dwarf stars. Teegarden B emerged from that effort, demonstrating the value of directing precision measurements toward stars once considered little more than astronomical background. The implications stretch far beyond a single discovery. Teegarden's star is expected to remain on the main sequence, the long, stable stage during which a star steadily fuses hydrogen into helium for roughly 8 trillion years. That is about 580 times longer than the universe has existed so far. While larger stars brighten, exhaust their fuel, and ultimately fade away, countless red dwarfs will continue shining across unimaginable expanses of time. But this immense longevity also reshapes our view of the future. If biology can emerge and endure around these enduring stars, then the overwhelming majority of life the universe will ever host may belong to worlds orbiting red dwarfs. The search has not lowered its standards. It has corrected its perspective, and Teegarden B stands among the earliest signs that the galaxy's most common stars may also become its most important destinations for discovery. Perspective often arrives through comparison. After spending so much time examining Teegarden B on its own terms, it helps to place it beside the other nearby worlds that have inspired similar hopes. The differences are surprisingly revealing. Distance alone does not determine which planet deserves the closest attention. The character of the parent star matters just as much, and sometimes even more. Proxima b remains the nearest confirmed rocky planet that orbits within the habitable zone of its star. Located about 4.2 light years from Earth, it circles Proxima Centauri, our closest stellar neighbor. Discovered in 2016, its estimated minimum mass is roughly 1.07 times that of Earth, immediately placing it among the most compelling exoplanets ever found. For a time, many expected it to become the leading candidate in the search for nearby life. But Proxima Centauri introduced a serious complication. It is one of the most active red dwarf stars yet studied, producing frequent flares and occasional superflares that release enormous bursts of radiation. Computer models suggest such activity could gradually erode or even remove a planetary atmosphere over immense spans of time. Early observations by the James Webb Space Telescope have not revealed evidence for a substantial atmosphere around Proxima b, although those findings remain preliminary and additional observations are still needed before firm conclusions can be drawn. Ross 128b presents a different picture. Orbiting a comparatively calm red dwarf, roughly 11 light years away, it possesses an estimated mass close to Earth's and follows an orbit within the region where liquid water could potentially exist. Its host star behaves much more like Teegarden's star than Proxima Centauri does. Yet, Ross 128b does not pass directly across the face of its star, from our viewpoint, making atmospheric studies with present technology extremely difficult. We know enough to be intrigued. We cannot yet know enough to be certain. The nearby stellar neighborhood offers further contrasts. Barnard's star, only about 5.96 light-years away, was once thought to host a promising planet after a reported discovery in 2018. Independent studies, however, failed to confirm that signal, and the candidate has largely disappeared from current scientific discussion. Wolf, 350 lies, roughly 7.78 light-years away, yet its powerful flare activity creates an environment considered far less favorable for long-term habitability, and no confirmed rocky planet occupies its habitable zone. A broader pattern gradually emerges. The closest red dwarf stars are often the most turbulent, exposing nearby planets to repeated bursts of energetic radiation. The somewhat more distant systems, including Ross 128 and Teegarden's star, appear considerably calmer. but calmness creates opportunity. Among nearby rocky worlds, these two planets consistently remain near the top of the shortlist for future atmospheric investigation. Teegarden B holds a slight advantage through its exceptionally high Earth Similarity Index and the increasingly encouraging portrait of its remarkably stable parent star. Absence can become a form of evidence when it persists long enough. For more than 70 years, humanity has listened for voices beyond Earth using increasingly capable radio telescopes, broad surveys spanning vast regions of the sky, and carefully targeted observations of nearby stars. Across countless hours of collected data, no signal has yet satisfied the demanding standards required to confirm the existence of extraterrestrial intelligence. That result may seem disappointing, but science treats every outcome as information. One moment came remarkably close to changing everything. On the 15th of August, 1977, the Big Ear Radio Telescope at Ohio State University recorded an unusually strong, narrow band signal near the hydrogen line frequency, approximately 1,420 megahertz. Hydrogen is the most abundant element in the universe, making this frequency a logical choice for any civilization wishing to announce its presence across interstellar distances. As astronomer Jerry Eman examined the printed data, he circled the remarkable sequence and wrote a single word beside it: Wow. The signal endured for roughly 72 seconds, matching the time that Big Ear naturally observed one region of the sky as Earth rotated beneath it. Then it disappeared. Every subsequent attempt to detect the same transmission at the same location failed. No confirmed natural explanation has fully accounted for it. No confirmed artificial source has been identified either. After decades of investigation, the famous signal remains an unresolved mystery rather than evidence of another civilization. But decades without confirmation have shaped astronomy in valuable ways. Every unsuccessful search narrows the possibilities and helps estimate how common, powerful broadcasting civilizations may be within our local region of the Milky Way. The silence has encouraged researchers to refine both their expectations and their methods. Instead of relying primarily on broad surveys that briefly sample millions of locations, many modern programs increasingly favor prolonged observations of carefully selected planetary systems judged most likely to reward patient attention. Teegarden's star belongs near the top of that list. Despite its exceptional proximity and the promise of Teegarden B, it has not yet received the sustained, dedicated listening campaign capable of detecting radio leakage comparable to humanity's own technological emissions across 12.5 light years. That opportunity still lies ahead. The instruments continue improving. So does our strategy. Meanwhile, our own presence has already begun expanding into the galaxy. Radio broadcasts, military radar, and countless forms of electronic communication have traveled outward at the speed of light since the early decades of the 20th century. Today, that expanding sphere extends roughly 100 light years in every direction. Teegarden's star has rested inside that growing bubble for many years already. But if anyone there possesses instruments sensitive enough to notice, our earliest broadcasts have already arrived. We continue listening through the same darkness, wondering whether recognition ever traveled back in our direction. At this very moment, a stream of ancient light is crossing Earth's path. Those photons left the Teegarden system 12.5 years ago, reflected from the surface and atmosphere of Teegarden B, before beginning an uninterrupted journey through interstellar space. They are reaching our part of the solar system now, Some continue past the planets into darkness. Others pass through our atmosphere, scatter across oceans and mountains, glance from rooftops and forests, and touch every landscape beneath the night sky. Their arrival is happening whether we notice them or not. Nothing about this is symbolic. It follows directly from the finite speed of light, the universal limit at which information travels through space. Every photon carries a record of the conditions that shaped it. Its wavelength, meaning the distance between successive peaks of the light wave, contains subtle clues about the materials it encountered before leaving that distant world. Hidden within those tiny changes may be hints of minerals, clouds, atmospheric gases, or surface ice. The information exists already. We simply lack instruments capable of extracting most of it. But that limitation is beginning to change. The extremely large telescope, expected to begin full scientific operations during the closing years of this decade or the early years of the next, has been designed with a collecting mirror unlike any built before. Its enormous light gathering ability may allow astronomers to separate a small fraction of the planet's faint glow from the overwhelming brilliance of its parent star. That achievement would not reveal forests, oceans, or living creatures, yet it could begin assembling the first rough atmospheric profile, providing the earliest direct glimpse into the chemistry surrounding that distant surface. Seen this way, Teegarden B stops feeling like a destination that belongs only to tomorrow. It is already communicating through physics alone. No transmitter is required. No deliberate message is necessary. Every passing second, the planet releases another expanding shell of reflected light into the galaxy. Earth happens to lie inside that endless wavefront, receiving it continuously as the years unfold. What reaches us tonight began its voyage before many events in our own lives had even happened. The world that produced those photons may already have changed in ways we cannot yet imagine, yet the information arriving today preserves that earlier moment with perfect fidelity. Space does not erase the record, it merely delays its delivery. But the greatest challenge is no longer distance, it is interpretation. Whether those arriving photons describe bare stone beneath an empty sky or an atmosphere shaped by living chemistry, the answer has already entered our neighborhood. We stand beneath its arrival every night, waiting for our technology to become capable of reading what the universe has been sending all along. Set every technical detail aside for a moment and keep only a single number in your thoughts: 12.5 light years. Nearly every conclusion we have reached about this neighboring world rests upon that modest distance. It is a number that feels immense to human experience, yet almost disappears when measured against the true scale of the galaxy we inhabit. The Milky Way stretches across roughly 100,000 light years, from edge to edge. Compared with that vast span, 12.5 light years represents only about 0.0125% of the galaxy's diameter. Cosmologically speaking, the Sun and Teegarden's star occupy the same small neighborhood. They belong to the same local corner of an unimaginably larger structure. When we speak of distant worlds, this one is remarkably close. That perspective changes everything. But human experience measures distance very differently. The fastest spacecraft ever built, the Parker Solar Probe, reaches peak speeds of about 163 kilometers per second, which is about 101 miles per second, during its closest passes to the Sunday. Even maintaining that extraordinary speed without interruption, a journey to Teegarden's star would still require roughly 23,000 years. Entire civilizations could rise, flourish, disappear, and leave only archaeological traces before such a voyage ever reached its destination. Light tells another story. A radio message transmitted from Earth today would arrive at Teegarden's star after 12.5 years. If someone there answered immediately upon receiving it, their reply would need another 12.5 years before reaching us. Even under perfect circumstances, with no hesitation at either end, one simple exchange demands a minimum of 25 years. You could ask a question as a young adult and receive the answer in middle age. But these numbers reveal something remarkable rather than discouraging. Physical travel remains beyond every technology humanity has imagined with practical engineering. Information, however, crosses that gulf with reliable precision. The earliest radio broadcasts from Earth have already washed across the Teegarden system, carrying fragments of our languages, music, science, and history into interstellar space. Whether anyone was there to notice remains completely unknown. For every generation before our own, this entire discussion belonged to philosophy rather than observation. Ancient scholars, medieval thinkers, and modern scientists all wondered whether another inhabited world existed beyond the sun, yet none possessed the means to identify a real destination they could imagine. They could debate. They could never test the question. But now we hold something profoundly different. We know the address, we know the distance, we know a rocky planet circles that nearby star. New observatories rising today will examine its atmosphere within the span of a human lifetime. 12.5 light years no longer marks an unreachable frontier. It marks the first threshold where one neighboring world may finally begin answering one of humanity's oldest questions. Imagine the announcement arriving after years of careful verification. Independent observatories compare their measurements. Separate research teams reach the same conclusion. The atmosphere of Teegarden B contains a combination of gases that resists every known non-biological explanation. Such a moment would stand above every previous scientific discovery, not because it answered every question, but because it confirmed that life had taken root beyond Earth. But the discovery would need careful interpretation from the very beginning. A biosignature would not identify cities, technology, or intelligent beings looking back across space. It would most likely point toward biological activity resembling the earliest chapters of our own planet's history. Earth itself supported life for roughly 3,500,000,000 years before any technologically capable species appeared. During most of that immense span, the world belonged almost entirely to microscopic organisms that slowly transformed the atmosphere through countless generations of metabolism. The statistical consequences would be extraordinary. Two nearby planets, each developing life independently within a region only 12.5 light years apart, would represent an astonishing sample despite its small size. That neighborhood occupies an almost negligible fraction of the Milky Way. If biology emerged twice inside such a tiny volume, the simplest explanation would become that life appears readily wherever stable conditions persist for long enough. But this would also reshape one of the greatest unknowns in the framework proposed by Frank Drake. The uncertain factor describing how often life begins on suitable planets would move much closer to certainty. Instead of representing an almost impossible accident, biology would begin to look like a common outcome of planetary chemistry, unfolding naturally when energy, liquid water, and favorable environments remain available across immense stretches of time. That realization would not reduce the value of Earth's living world. Quite the opposite. You and we would see our planet as part of a much larger pattern extending across the galaxy. Every forest, coral reef, grassland, and microscopic ecosystem would become evidence that the universe possesses a remarkable capacity to organize matter into living systems. Earth would remain precious, while also becoming wonderfully less isolated. But scientific discoveries never remain confined to laboratories. Philosophers, historians, artists, and religious scholars would spend generations exploring the meaning of a second living world. Long established ideas about humanity's place in the cosmos would not disappear overnight, yet they would inevitably be viewed through a broader perspective. The conversation would expand rather than end. Governments would notice as well. Research agencies, universities, and international partnerships would almost certainly direct unprecedented resources toward astronomy, planetary science, and astrobiology. New telescopes would be planned, more ambitious observatories would follow. Missions once considered distant possibilities would become urgent priorities. A confirmed biosignature on Teegarden B would not close humanity's oldest question, it would transform that question into the central scientific pursuit of our age. There is another outcome that deserves exactly the same careful attention. After years of observation, increasingly sensitive telescopes may examine the atmosphere of Teegarden B and find no convincing sign of biological activity, no sustained oxygen, no methane existing alongside oxygen, no persuasive chemical imbalance pointing toward living processes. They may even discover that the planet possesses little atmosphere at all, leaving its surface exposed to the conditions of space. But such a result would require just as much discipline in interpretation as a positive one. It would not demonstrate that life exists nowhere beyond Earth. The galaxy contains hundreds of billions of stars, each with its own history and possibilities. One world, however promising, cannot represent them all. Science would resist drawing conclusions that reach beyond the available evidence. Even so, the implications would be profound. We have spent this journey assembling a picture of Teegarden B as one of the strongest nearby candidates for habitability. Its Earth Similarity Index approaches our own planet. It has likely existed for around 8 billion years, providing an immense span during which biology might have emerged. It circles a comparatively calm red dwarf, and its gravity appears broadly similar to Earth's. If such a world remains lifeless, the assumption that biology follows naturally from suitable conditions becomes much more difficult to defend. But the evidence would not stand alone. It would join the growing picture provided by the planets orbiting the star known as TRAPPIST-1, where observations have already suggested that some rocky worlds may lack substantial atmospheres. Together, these findings would begin forming an early statistical pattern. Suitable orbits and rocky surfaces might prove insufficient. The transition from chemistry to biology could itself represent the rarest step in the entire sequence. That possibility reaches far beyond astronomy. It would suggest that Earth's biological history, stretching back roughly 3,800,000,000 years, reflects an event of astonishing improbability rather than an ordinary chapter repeated throughout the cosmos. Every living organism, from microscopic bacteria to forests, whales, birds, and human beings, would become part of an exceptionally uncommon lineage. Consciousness itself might represent one of the rarest outcomes the universe has ever produced. But notice what would remain unchanged. The galaxies would continue their slow revolutions. Stars would still form from clouds of gas and dust. Gravity, light, and time would follow the same laws they obey today. The physical universe would appear exactly as it always has. Only our understanding of life's place within it would shift, placing extraordinary weight upon the single biosphere we already know. Whether the answer ultimately points toward abundance or rarity, its importance cannot be measured only in scientific papers or telescope observations. It will reshape how we understand our origins, our future, and the value of every living thing that has ever existed on this small world we call home. Some questions change simply because they move closer. Distance has always shaped how we think about possibility, separating imagination from investigation. A mystery beyond every practical reach can remain fascinating for centuries. A mystery waiting just beyond the reach of our instruments becomes something entirely different. It becomes part of the present, inviting us to examine it with patience rather than speculation. Imagine, instead, that the nearest promising world existed 100 million light years away. Such a possibility would inspire books, debates, and dreams. Yet no telescope planned within our lifetimes could hope to test it directly. The question would remain philosophical, resting on probability rather than evidence. We could discuss it endlessly while knowing that no observation would settle the matter for generations beyond counting. But Teegarden B stands only 12.5 light years away. Compared with the immense breadth of the Milky Way, stretching roughly 100,000 light years across, that distance represents about 0.0125% of the galaxy's diameter. Cosmically speaking, this neighboring world occupies the same local corner of the galaxy as our own Sunday. It is close enough that every improvement in astronomy feels directed toward a real destination rather than an unreachable dream. That nearness changes the character of the question itself. We are no longer wondering whether life might exist somewhere among uncountable stars. We are asking about one confirmed rocky planet with a known orbit, a measured mass, and a specific address in the night sky. You can point a telescope toward it. You can calculate when its light departed. You can build instruments designed with that exact world in mind. But proximity also increases responsibility. A question that can eventually be answered demands greater care than one destined to remain forever uncertain. Every observation, every spectrum, and every refinement of our methods becomes another step toward replacing assumption with knowledge. The conversation grows more disciplined because the evidence is gradually coming within reach. Human history has already experienced several profound shifts in perspective. We learned that Earth circles the Sunday. We discovered that our solar system occupies one ordinary region of a vast galaxy. Later, we found that the Milky Way itself is only one among countless galaxies filling the observable universe. Each adjustment initially unsettled familiar ideas before becoming an accepted part of humanity's understanding. Accuracy replaced comfort, and our view became richer. But Teegarden B does not yet force another transformation. For now, it remains a carefully measured question waiting at the edge of what we can observe. If that question ultimately receives an answer, the final adjustment may concern neither distance nor size, but companionship. We may discover that life belongs naturally to the universe, with Earth sharing a greater community than we imagined. Or we may learn that this living world carries an astonishing rarity, making every breath, every forest, and every conscious thought part of something almost unimaginably uncommon. Time gives ordinary places extraordinary depth. A single world can appear unchanged from our perspective while carrying a history longer than almost anything we can truly imagine. Teegarden's star has shone for about 8 billion years, steadily converting hydrogen into light, occupying its modest place within the Milky Way, while generation after generation of stars, planets, and galaxies continued their own stories elsewhere. That patient star has illuminated Teegarden B, throughout nearly all of that immense span. Every sunrise on that distant world, if skies and horizons exist there, has come from the same small crimson sun. Every season, every geological change, every shifting atmosphere has unfolded beneath its enduring glow, but the star itself has never hurried. It has simply continued burning, year after year, across stretches of time that exceed ordinary human understanding. Consider what that means beside our own history. During roughly the first 4 billion years of Teegarden's star, Earth itself had not yet formed. For about the first 5.5 billion years, no ancestor of humanity existed anywhere. During almost the entire lifetime of that neighboring system, no mind on our planet possessed the knowledge that such a place even existed. We have known of Teegarden B for only a handful of years. It has existed through billions, but the universe has never paused while waiting for observers. Stars ignite without witnesses, planets cool without audiences. Oceans may appear, climates may shift, and perhaps living systems may emerge without any intelligence elsewhere recording the event. Reality continues whether it is measured or not, carrying its own history forward with complete indifference to discovery. Suppose life began there around 6 billion years ago. Such a biosphere would have already experienced a duration exceeding the entire age of Earth itself. Countless evolutionary paths might have unfolded before the earliest microorganisms appeared on our planet. Entire chapters of biological history could have passed long before the first fish entered Earth's seas, before forests covered continents, or before curious primates lifted their eyes toward the night sky. Or perhaps none of that happened. Perhaps Teegarden B remained an empty world throughout those same billions of years, shaped only by geology, chemistry, and the persistent light of its star. Even that possibility carries remarkable significance. It reminds us that immense age alone cannot answer every question about life's emergence. Time creates opportunity, yet opportunity does not automatically become biology. But this neighboring planet ultimately asks something even larger than whether organisms inhabit its surface. It invites us to compare the age of the cosmos with the astonishing brevity of awareness itself. The universe is estimated to be about 13,800,000,000 years old. Human curiosity occupies only the thinnest fraction of that timeline. We arrived near the end of an unimaginably long story, opened our eyes, and discovered that one nearby world had been waiting all along, carrying its answer through the ages before anyone existed to ask the question. Begin with an ordinary human moment. A researcher studying asteroid observations in 2003 noticed a faint star whose large motion across the sky had escaped earlier catalogs. That careful observation eventually revealed Teegarden's star, a nearby neighbor that had remained overlooked despite its relative closeness. One attentive decision became the opening line of a much larger story. Years later, another chapter unfolded in the mountains of Spain. There, astronomers designed and refined an instrument capable of measuring radial velocity, the minute back and forth motion of a star caused by the gravity of an orbiting planet. The movement they sought was astonishingly small, slower than an easy jogging pace. It demanded extraordinary stability, relentless calibration, and remarkable patience. Over 3 years, about 200 separate observations accumulated until a consistent pattern emerged from the measurements. But discovery did not end with finding a periodic wobble. The observations became calculations, the calculations became evidence, and the evidence became a scientific paper read by relatively few people outside astronomy. Within that publication appeared a single number, 0.95, representing the Earth Similarity Index, a comparison showing how closely Teegarden B resembles our own world in several measurable physical properties. Behind that simple value stood decades of engineering, observation, and mathematical care. Now consider what remains before us. An enormous mirror, almost 128 feet across, which is about 39 meters, is taking shape in the Atacama Desert. Every polished segment, every adaptive correction, and every precisely aligned instrument exists for one purpose: collecting enough light to reveal details previously hidden within distant worlds. Years of observing time may be devoted to one faint point among countless stars before astronomers feel confident enough to draw careful conclusions. But this story contains no spacecraft crossing the darkness. No crew will step onto Teegarden B within our lifetimes. The journey happens differently. We extend our reach through mirrors, detectors, mathematics, and disciplined observation. Human curiosity travels where our bodies cannot, stretching across about 118 trillion kilometers, which is about 73 trillion miles, without leaving Earth itself. Nothing else we know performs this act. A species that has existed for only a few 100,000 years learned to measure invisible motions around another star and to ask whether chemistry there resembles the chemistry that transformed our own planet. Such a question could not have been asked even 100 years ago. The capability itself is astonishing. Whether Teegarden B ultimately reveals living chemistry or an empty atmosphere, the reaching remains deeply significant. We have become a civilization able to investigate another world with evidence rather than imagination alone. You and I live during the brief moment when that transformation is taking place, when curiosity has matured into measurement, and when the universe is beginning to answer because humanity finally learned how to ask. Somewhere beyond every uncertainty we still carry, the answer already exists. It does not wait for our conclusions or depend upon our experiments. Reality reached its own conclusion long before we learned that Teegarden B existed. Our observations will not create the truth. They will simply uncover what has always been there. At this very moment, Teegarden B continues its journey around its ancient red star, completing one orbit in about 4.91 days. Whether its surface is bare stone, deep ocean, frozen plain, or living landscape, that condition is already real. The planet remains governed by gravity, chemistry, and light that continue without interruption. The universe has never paused while humanity searched for understanding. But the uncertainty belongs entirely to us. The question remains open only because our knowledge remains incomplete. Nature is not hiding its answer. Every ray of light leaving that distant world carries information about the place it reflected from, preserving subtle details within its wavelengths. We have simply reached the edge of what our instruments can presently decode. This places humanity in an extraordinary moment, unlike any before it. For almost all of recorded history, questions about life beyond Earth belonged to philosophy, religion, or imagination. Now the question has acquired an address. It occupies one confirmed rocky planet at a measured distance, close enough that observatories already under construction may begin revealing its atmosphere within the span of a human lifetime. We are approaching an answer through observation rather than speculation. Light reflected from Teegarden B has traveled for about 12.5 years before reaching Earth. That journey covers roughly 118 trillion kilometers, which is about 73 trillion miles. Some of those photons are entering our atmosphere even now. They fall across mountains, oceans, cities, deserts, forests, and every place where people continue their ordinary lives. Hidden within them lies either the chemistry of a living biosphere or the record of a world where biology never appeared. We simply have not yet learned enough to read the message completely. But whatever that message contains, the universe owes us nothing. It is under no obligation to produce neighbors, companions, or confirmation that life flourishes elsewhere. It is equally under no obligation to leave us alone. Stars burn according to physics. Planets evolve according to chemistry. The cosmos does not shape itself around human expectation. Yet something remarkable has happened here on Earth. We became a species that refused to stop wondering. We built mirrors larger than buildings. We invented mathematics capable of measuring worlds we cannot visit. We learned to recognize another planet by watching the tiniest movement of a distant star. Then we turned all of that patient knowledge toward one faint point of light and asked, with genuine evidence finally within reach, what is truly there? Whatever answer eventually arrives, the act of asking belongs to us, and that reaching may be among the greatest expressions of what it means to be human.